All right, so in this section, we're going to look at machines. Okay. What is a machine? We'll look at machines, we'll look at how efficient machines are. So we've talked about work done. Okay. So now let's look at how the concept of conserving energy, work done applies to machine. So a machine is any device, right, that allows us to do work. For example, if you input an energy into a machine, right, the work that you input must be at least equal to the work output. So the work that is taken out of the system. So the work that is inputted into a system must be equal to the work that is taken out of that system. Now, if you remember what work is force times distance. So the input force times the input distance must be equal to the output force times the output distance. That's a simple principle here. Work input equal work output. Okay. Now, if you remember the kinetic energy and momentum, the relationship between the two, what you realize is that both kinetic energy and momentum, they all depend on mass and velocity. They all depend on mass and velocity. So momentum depends on mass and velocity, right? Kinetic energy depends on the mass times the velocity squared. Okay, so if you look at both kinetic energy and mass, you realize that they all depend on mass and velocity. Now, momentum is a vector quantity, right? While kinetic energy is a scalar. So remember, vector quantities, they have a direction, while scalar do not have a direction. Now, coming back to the conservation of energy, right? You realize that energy is conserved uh, uh, in everyday life. People might say conserving energy means to save energy, right? Like Edison, the energy company, usually during summer, they say try to minimize the amount of energy that you use in order to save energy. But when we're talking about the law of conservation of energy here, uh, what we mean in physics is that the amount of energy remains constant. It remains unchanged. So in the absence of an external work input or output, the energy of a system remains unchanged. Energy cannot be created, energy cannot be destroyed. Always remember that. Now, if we consider the system of a bow and arrow, if you know a bow and arrow, in drawing the bow, we do work on the system and it gives it potential energy. When the bowstring is released, most of the potential energy is transferred to the arrow as kinetic energy and some of it as heat. The reason why we say most is because not all of it, right? The frictional force takes some of that energy off as heat. Okay, so energy is not created, energy is not destroyed, it's only transferred from one form to the next. Now, suppose the potential energy of a drone ball is 50 joules and the kinetic energy of the arrow is 10 joules. Then, if the energy input is not the same as the energy output, then part of it, right, the 10 joules goes to the warming of the ball. So some of it will be lost as heat, but some of it is transferred as heat, uh, transformed to heat, but it's never lost. Okay. Now, coming back to the concept, applying that concept now to machine. So, what is a machine? It's just a device for multiplying the force or changing the direction of a force. So, no machine can put out more energy than is put into it. So, a machine does not create energy. Okay, so the machine just uses the energy that is being input to do what? To maybe multiply the force, to make the force bigger so that the force can now do more work. Okay. So you cannot create energy. Okay. You can't. So it just creates energy A machine cannot create energy. What it does is that it only transfers it or transforms it from one form to the next. So energy, I mean, work input is called work output. Okay, work input is called work output. So you have a force times distance. Input is equal to force times distance output. Example is a lever. So if you look at a lever, as you see the images here, you see that you see a small input force over a long distance is equal to large input force over a short distance. So everything balances out such that the work input is equal to work output. Okay. So in an ideal pulley system, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 Newton. For every 1 meter length of rope she pulls down, the crate rises, of course, 25 centimeter. Okay. For every 1 meter length of rope she pulls down, the crate rises 25 centimeter. The whole idea here is that the work input should be equal to the work output. Okay, work input should be equal to the work output. Now let's look at efficiency. So again, the way I want you to look at it is how effective is that machine? When you put in 100% of work, do you have 100% of work that comes out? That's the point. That's how efficiency is. If some of the energy is lost, or if some of the energy does not go to do the work, then some of it is lost and that reduces the efficiency of the machine. So how effective a device transforms or transfers useful energy. Again, useful energy. If some of it is transferred as heat, heat is not a useful form of energy. Okay. So a machine with a low efficiency is one in which a greater amount of energy is wasted, right? Because when you put in energy into a machine, you want it to do a particular task and you want it to do it efficiently. So if you put in work, if you put in energy into a machine and not all of it goes to for a particular purpose for which it was intended and some of it is just wasted, then that machine is not efficient. Some energy is always lost as heat, but we want to make sure that efficient machine only loses a very small amount of it as heat. So a certain machine is 30% efficient. This means the machine will convert 30% of its energy input to useful work. 70% of the energy input will be wasted. Right? That's true for A. Because if you are 30% efficient, it means that 70% of your energy is wasted. Means it's wasted. Now, sources of energy. Let's look at sources of energy here. You have energy sources. Example is the sun. Okay, the energy from the sun. So it does so much work. Remember, it evaporates water, it helps to dry surfaces. Water falls as rain, rain flows into rivers, into generator, then back to the sea to repeat the cycle. So solar energy can transform into electricity by voltaic cells. Solar energy indirectly produces wind that can power turbines and generate electricity. So sources of energy. So you have a dry rock geothermal power. It's a producer of electricity. So in a geothermal station is a station that transforms the heat from the earth core or the heat from beneath the earth surface into a form that's more useful, like electricity and so on. You have solar power. The power available in sunlight is about 1 kilowatt per square meter. Example of it, you see many people, especially in California, are shifting towards solar panels. This is because these solar panels contain voltaic. cells that are able to transform energy from the sun into electricity. So you have hydroelectric turbines, wind turbines, bio-based fuels. Energy storage and transfer. Um, Electricity synthetic cell can be created from bio-based product. So you have hydrogen. Hydrogen is not a source, but can be generated from multiple sources, and is a good fuel for fuel cells or internal combustion engines. So this is hydrogen creation. So when electric current passes through conducting water, bubbles of hydrogen forms at one wire and hydro and oxygen at the other wire. This is called electrolysis. Okay. All right. So again, energy in sunlight is converted to electrical energy. So if you look at the cells, this is an example of a solar plant. So many solar cells generating electricity to power up a city. So that's that for this. Thank you. Make sure you're taking down your notes so you can do your assignments well.